My name is Olaf Weiser from IBM, and usually I spend my working time with designing and implementing environments, infrastructures with very specific requirements for high performance computing. And so today I try to cover in the next 20 minutes how an ESS, IBM's Elastic Storage Server, this is just a name, may help you or can help and support to raise performance for sync and share environments. And before I bothering you with too much technical details, I thought it might be a good idea to start with a little anecdote to bring us all on the same page. Just imagine you have any fancy application up and running, and this is your first user. There's a little penguin there, and this is our infrastructure, maybe consisting out of some application servers, databases, and piece of storage. And easy to explain, self-explaining, obvious. What happens now? So you start rolling, and now you see what happens. More and more users get on a train and accessing your application, and it raises the pressure in your data center. And like I said, it's obvious what happened now. And the more users you're joining, the more pressure you raise inside of your data center. And even worse, I mean, if you have a well-functioning, perfect working application, this strange human being called user will request new features, and it raises the pressure again. And so we all know, I think we all know, we have challenges in terms of scaling issues, scale in your application layer and maybe database. And I will focus now on this motivation, how can we scale? And I mean, we all know what happens if you don't find the right answers for these scaling issues. Maybe you bother your users. That's what's the motivation about my presentation now. So we focus in 3 steps, how maybe an ESS spectrum scale may help you here in terms of scaling issues. So in a more technical view, where we are, I divided in three layers. Let's say the application in the middle, the client side at the end, and at the bottom we are with spectrum scale, and there's the namespace, the real storage. Self-explaining and obvious. Automatically, with no action, it will scale at the end user level. That's not a big thing to understand. And it may challenges you in the mid layer. You have applications and databases which need to be ready for these scaling requirements. And I will focus on the lower level, on the infrastructure now with the spectrum scale. So if you have to decide, maybe you take a parallel file system, if you take a file system at all, if you take a shared, if it's parallel, you need to cover recommendations in terms of capacity, availability, robustness, maintenance, all these things. And finally, all what matters to resist what your user expects is performance. If you're too slow, I mean, nobody else from the upper layer will accept this solution. And with spectrum scale, our long history, it's more than 15 years now, we have our history in HPC workloads. It means real high performance data. The file system and the data taking and managing is designed for high performance data. And for streaming data, we have various types of workloads we can satisfy with the file system, and it's completely process compliance. So I will focus now what I highlighted here in this red part. This is the infrastructure which comes with spectrum scale. So it's just storage blocks, definitely finally at the end the namespace, and it also stretches over networks. So we talk a complete infrastructure stack at this point. And if we have something in place like this, we can continuously, maybe I give a little outlook about integration. If we have a powerful fundamental storage environment, maybe we can help you integrate your applications to make this run more smoothly, and you can add and integrate other data for any other workload in your environments. So to spectrum scale and ESS. Before I start to show some pictures what the ESS looks like and physically, some background information. All what matters from your application point of view, an application now, I target this type of application you're using in a Sync and Share environment, you access some files or some things in a namespace. It's here. And as we all know, the files were stored physically on some block storage. And there's a long way in between. You talk to a namespace, but under the namespace you have file systems, you have operating systems, you have network interface card, you have maybe host channel, an adapter to transfer something, you have transport layers, networks, then you have backends, and below the backends there's cache and other algorithm, and then you have some block storage. It's a long way. The more components are involved in this picture, the more handover, the more breaks you have, the higher the likeliness that you lose performance, that you become more and more inefficient on this place. Even more important, if you have a need to scale, what happens now? You talk to the same namespace, but you have to cover all these layers all through. And this raises the challenge even more to think about how to cover these layers all together. I mean, I say it out clearly. This is not spectrum scale, obvious. No? I make a little example here in the middle, how to solve this easily. It looks the same, that all applications have access to the same namespace, but it is backed on disk just by a single guy, and you need additional protocols in between to share the access to the data. It may work, and it works perfectly fine, we all know that, but does it work fast enough? That's the question. And even more, if you now need to scale, I mean, you can scale a little bit in terms of disk and capacity, but I mean, what a waste of money and technology if you buy and add some low latency storage materials like flash, SSDs, or NVMe storage technology. I mean, just by these protocols, you are limited in capacity, in availability, and all this stuff. So this is more or less, it may help you out until a certain point, but then you are dead, it's a dead-end street. Therefore, we now focus on spectrum scale. What is spectrum scale? Spectrum scale is a complete parallel file system, easy to explain. You just need some code on every machine in your environment. The code is available for various operating systems, AIX, Linux, you name it. And you design a file system out of these codes. So instead of installing NFS or SMB or whatever, it's just GBFS now. And one main key feature here is that with this code, we share the access to the disk. So we do not share the namespace. This is the final result, that it looks like this. We share disks. And this means every member in this grid has the same access to the physical block devices. Therefore, it's a real parallel file system. We are completely POSIX compliant with various additional features, snapshot, quota, whatever, you name it. The list is long, very long, longer than I can talk here in 20 minutes. For now, we focus on high efficient RPCs we send from here to access the disk. And as I said, we are completely POSIX compliant, so you can use it with every application you have in your mind. This allows us to build, and in fact we really do this, huge environment with thousands or hundreds of clients accessing physical storage from storage controller or whatever, internal disk. We take every block device we can get and talk directly with all clients to that. So, and now an ESS you can think of is exactly this. We take some nodes connected to some disks and plug it into our environment. And back to the beginning of this talk, with an ESS, I cover all these different layers just with one piece of software. That means less handover, less breaks, all the way through from the namespace to the disk is under manage and control within an ESS. Well, so more focused or more in detail spoken, we have two servers running our code with MMFSD. That's spectrum scale, it's just an RPM, you can install it. That's real native software-defined storage, just another word for this. And has access to the disk. These are just JBODs, JBODs or JBOF, just a bunch of flash or this. We have various vendors implemented, but mostly common, pretty common is the LSI, high density enclosures. And then within this amount of disk, we allocate disk space. We call it vdisk. You can compare it with a LAN, something like this. And we we allocate this from here and provide this for the all members in the cluster. Zoomed a little bit more in this picture, you can imagine like this. You have here a bunch of disks, that's are the physical drives. And now we allocate this space here with various erasure code levels. 8 plus 2p, 8 plus 3p, 2, 3, 4-way replication. I mean, you could allocate this unreplicated, you can do that. And it's completely wide-striped among all these drives. That means we can cover different quality of service level, different KPIs in terms of redundancy and performance, response time, whatever. I mean, a 3-way replicated with a smaller block size maybe react faster than an 8 plus 3p, 10 block size, 8 megabyte in terms of small I/O, things like that. So you can mix it within the same physical disks and allocate according to your needs, your space. This completely wild-striped method to allocate space has another advantage. I'm sure all of you know this nasty little thing, degraded RAID. So from my point of view, RAID is dead because nowadays we have 8 or 10 terabyte drives, and we cannot prevent that the drive will fail or misbehave. These are physical technique and it breaks. So what we can do is to ease the pain if a disk breaks, and exactly this happens here, and I try to explain this. So assuming we have an 8 plus 3p erasure code wild striped among these disks, and let's say we have one disk enclosure, 4 units, that means 60 drives in there, and we have 3 faults. I pull out the tray and remove 3 disks. So then I have almost 20% which are affected by 1 fault, 3% which are affected by 2 faults, and only less than 1% are affected by really 3 faults. These are critical, the others not. I flip back. For those who left school long time ago, it's easy to calculate. 11 out of 60 is 80%. Then the likeliness of having 2 faults is 11 out of 60 times 10 out of 95, 3%, and 11 out of 60, you can read it on your own. So less than 48%, 0.48% are affected by 3 faults. That means if I do the RAIDs in software, I have the knowledge and the control over the RAIDs. And now I do the following thing. I have the approach that I make a difference between being critical or being non-critical. And that means we cannot avoid that the disk will fail. I mean, the likeliness to have 3 faults in a row all at once, it's very unlikely. But even if so, we can rebuild this little fraction of data with less than 5 minutes, regardless if you have 6 terabyte drives or 8 terabyte drives or whatever. It's in the code done by logic. Next thing, come back and focus more on performance, what you're interested in. With providing the namespace out of the ESS, we directly serve on the file system layer on the client-side client. In this case here is the NSD client and the GBFS client. Your application may run on the client layer, and here you may have various types of workloads. You have random workloads, databases, maybe you have streaming workloads, and the guy who is closest to your application is the NSD client part of our code. And he has various code detection algorithm to predict some workload here at this place and hand over by efficient RPC protocol these blocks, these requests to our ESS. You have various block sizes I explained already. And what happens now is that in the ESS pushes the data or fetches the data down from disks. So the workload detection happens here. And from the point of view on a disk level, all I/O is completely random. So there is no loss of performance whether you have a random workload or a sequential workload, because on the disk layer, every I/O is a random I/O because it's completely wide-striped. The next block is never fetched from the same disk. So that's why we can raise performance. Usually I would explain a little bit more about the connectivity layer from here to here, but 20 minutes is not much time, so I skipped it. If you have questions, you can ask us. So now, to give you an idea what it looks like, we have several models. All these explained features and technology is in software. However, we bundle the software. You can install the software on any client, on any machine you run, but we bundle this software in every time with 2 nodes, and then with various choice of how many disk enclosures. We have nearline SAS disk enclosures, the LSI, we have SSD drives, and just with the SanDisk flash and RAW 3 units of height with 8 terabyte flash DIMMs in there. So you can pick the right model, what fits best to your requirements in your environment. That's the first thing. The next thing is you can combine these things. That means it's a building block approach. So if you ran out of space, IOPS, capacity, whatever, you can scale horizontal and bring in the next building block. And if you can do it on a very flexible choice, it means if you ran out of IOPS, you will rather go on this side with some flash-based or SSD-based models. If you ran out of capacity, you add a building block from more or less this side. So it's very flexible. So there's no limit anymore in your namespace because you can put in capacity or IOPS, whatever you need. Some toughs about numbers. I mean, it's nice to see all these features. What can you expect? What is the benefit to get out of it? I prepare some slides to give you an idea. One building block, ESS GL6, so that's the model with 6 enclosures with nearline SAS drives, can saturate nearly 30 gigabytes per second on read access and nearly 23. That's just a simple test with GBFS perf. And here, GBFS perf, and here I documented what I did in the command line. So I mean, this is close to the limit of the SAS drive, of the SAS bandwidth. For write, we have to sacrifice a little bit of the performance for writing parity and things like that. For parallel workloads, you see that scales well. I spent extra charts to demonstrate that we do not only we are not only saturate the bandwidth with parallel I/O, also for single workloads, for single client access. I would say we are very high. We can read and access data with a high performance. That's an example of a single client accessing files or whatever on a GL6 model. It's 10 gigabytes per second with a single client. Maybe here, some side effects focus on the connectivity. I mean, 10 gigabytes is the ability of the codes talking to from client to server and vice versa. To get out these huge bandwidth from this disk, it wouldn't be possible with a 10 gig or 40 gig network. So therefore, consider InfiniBand infrastructure as well. On the other hand, with latest codes, we raised this number to 16 gigabytes per second with a single client access to the data. Okay, things you may be more interested in is metadata performance. So I spent a chart what the code is capable of doing with the MD test. Maybe some of you know the MD test. With last recent code, we can, in a shared directory, that means shared directory, and I think 11 clients. In a shared directory, we can create 40,000 files per second and almost 5 million stats in a shared directory. If you can streamline your workload, and I mean it depends on your application, I gave you the number for non-shared directory. It's nearly 350,000 file creates per second, and you can read yourself so almost 1 billion stats on a file. So maybe this type of workloads is more in focus in a sync and share environment, and it's all native in your namespace. It's a regular POSIX compliant file system. So this brings me back to the beginning. Now, if you have an environment like this within ESS, spectrum scale environment, we can think about, we take data which we get from any other workload, HPC, streaming, you name it, photo science, whatever, and make it available to our sync and share environments. My approach is that I say we have various APIs available to plug in on spectrum scale. That means we have an Hadoop integration, we have Docker integration, we can talk OpenStack, Swift, you name it. And let's say we rely on our massive metadata performance. That means, these numbers I recently showed you, will maybe help you to accelerate your client-server sync and share application to access the data. I have an example here as well, prepared. Metadata performance. First of all, just what you should know already. In a regular POSIX file system, the metadata is completely wild-striped. The inodes were allocated somewhere on your disk, and a directory block, even worse, it's a real standing block on disk somewhere in the namespace. So finding files, screening your metadata is a very expensive operation, and it's hardly to parallelize. Even if you put everything in memory, and if you have a file with a file system, a namespace with millions of files, 10 millions of files, or even billion, it means in a case like this, with POSIX interface, it means millions of IOPS to generate. Even if you talk to memory, it will waste time. So you can accelerate this with hardware, with memory, flash, whatever, but you can do things better with Spectrum Scale. We organize metadata differently. It's all our metadata is organized in a hidden file sequentially. So continuously blocks, one after the other, offset 0. And depending on the block size, which can be chosen freely from 1 meg to 16 meg, we can organize the metadata sequentially. By being a parallel file system, like I explained, parallel access to the disk, now we can screen this metadata in parallel and sequentially. That means the more nodes are in the cluster, the more parallel access you have. If you have 100 nodes, you divide the metadata space into 100 fractions, and you get the response much quicker. That's our approach, and I have a little demonstration here. I have time for this. During regular operation, that's the DESI file system in Hamburg. During normal operation, I kicked on the policy. I highlighted a little bit because it's hard to read. I kicked on the policy, just find all files. That's the starting time, that's the end time. That means 1 minute. 1 minute for 2.5 million files and 200,000 directories, as I said, during normal operation. So this is something you can expect. And during that time, we can write extended attributes. We can we can modify extended attributes, all these fancy things. And as I said, it scales. So if you see there's a lag on response times, in your case, just put in another building block and you will be faster. Next thing is, we did the same thing with a completely empty GL6. GL6 with nearline SAS drives, no memory, no flash. It's just poor, stupid, cheap nearline SAS drives, but with no workload on it. And we did the same thing with 1 billion objects, and it's in 8 nodes, and it finishes in less than 2 minutes. So this is something you can have in mind if you design your next slides. Environments. Maybe it will help you. That's it. I hope it was not too boring for you, and if you have any questions, I mean, there's more features and functions in it that I could explain in hours.
Thank you, Olaf, first of all. While the next speaker prepares, I don't know Tom. I think that we have time for a question.
Thank you. Olaf, thanks a lot for your talk. We are just cooperating, ETH Zurich, with our Institute of Technology, together with IBM. We purchased this Spectrum Scale, and we will get our data, our sync and share data in Spectrum Scale. And I hope that within the next CS3 workshop, we can report good results, as Olaf already mentioned in his talk. Thank you.
Thank you. I hope so.